and welcome to new topic, which is SAR interferometry, or in short we also say InSAR. When we have started discussing about active microwave remote sensing, at that time once or twice I have referred this SAR or interferometry or InSAR. So, this discussion is in two parts. So, first we will be discussing about the technology itself, that how InSAR works, and then we will be seeing some examples or applications of SAR interferometry. Basically, if we see the what is exactly interferometry, that in what we do in SAR interferometry or radar remote sensing, that we observe the area, same area, from slightly different look angles. So, when this is done, then you are having a pair basically. So, this can be done simultaneously, like it has happened in case of SRTM, with the two radars mounted on the same platform through a shaft, or it can be done with two different timings through the repeat orbits of the same satellite, same sensor over the same area, only there will be a time difference. So, if I take example of say a ERS satellite or a NVSat satellite, then these satellite used to visit the same area after 35 days. So, then you can have a pair with the slightly different look angles of the same area through same platform, and that pair then can be used in interferometry. So, a pair is definitely required. So, SAR interferometry basically allows us to measure, because radar remote sensing is a radio detection technique. So, it basically allows us to measure of the radiation which travels through because of his coherent, and this plays very important role, the coherent, which we will be discussing further on this. And this measurement of travel path, which is once a pulse or energy has been sent by the sensor, and then the variations which occur in between are a function of satellite position and time of acquisition, which allows the generation of the most common product of SAR interferometry is digital elevation models. This is what exactly done in case of SRTM, Shuttle Radar Topographic Mission, that 80% of the globe was covered except polar regions, and these pairs were then analyzed, processed, and then finally digital elevation model at different spatial resolutions were created for almost entire globe. And also, apart from allowing to generate digital elevation models, these pairs, or through SAR interferometry, we can also get the deformation information of centimeter accuracy, or even if processing is done and other conditions are fulfilled, then we can get even millimeter accuracy in our measurements or estimations of ground deformation or surface deformation of the terrain. So, there are two main applications. One is of course digital elevation model, another one is to detect the deformation which might be caused due to maybe landslide, maybe subsidence, maybe earthquake, and there can be many factors. So, now we will be seeing that how these the pair is acquired. In this figure, what we see that satellite is passing through this orbit 1 and having a particular look angle and looking the same area, as you can see that it is antenna footprint is shown here. And this these directions are basically the slant range of different orbits. So, if I talk about the first orbit, then this is the slant range, then there is a second orbit, and then slant range is here with two different slant ranges, but or look angles, but the area which it is covered is the same. So, same area is covered through two different orbit or orbital passes having might be little different look angle, and the perpendicular distance between these two these slant ranges, that is called the perpendicular baseline. Baseline is very important. Baseline is very important to drive either a highly reliable digital elevation model or accurate digital elevation model or ground deformation also. So, the baseline should be to optimum in length. If it is too big, the number is too large, then probably we will not have the coherence between these two scenes, which will be acquired by these this satellite through two orbits, and then we cannot generate interferograms. So, baseline becomes very important. Now, this is basically the flight direction which we are seeing. So, this arrangement is there in SAR interferometry, and the satellite or the sensor should be capable of acquiring the data of the same area, maybe little through different look angles on successive orbits. That's the thing here. So, the distance basically, as I was mentioning, that is the baseline, perpendicular baseline, and there is also a interferometry baseline. So, basically the distance between the two satellites, as you are seeing in orbits, in orbit 1 and 2, in the plane which is perpendicular to the orbit is called the interferometry or interferometer baseline. And whereas the projection which is perpendicular to the slant range, as I mentioned earlier, that perpendicular to this slant range, that is called the perpendicular baseline. And this perpendicular baseline, as I have already told you, is very important to drive interferograms from a pair. So, SAR interferograms basically are generated through this processing which is called cross multiplying, and that too pixel by pixel. So, pixel of orbit 1 scene and then pixel of orbit second scene, and so that means the co-registration of a very high quality is also very much required in the SAR interferometry. So, using this cross multiplying, the first SAR image which we with the complex conjugate of the second, this is how it becomes, and one image we can take as a master image, another one we can take as a slave image, and by this, in this example, like the first image with the complex conjugate of the second. And then interferogram, basically the interferogram amplitude is the amplitude of the first image multiplied by that of the second one, and whereas its phase, the interferometric phase, is the phase difference between the images, and this phase difference is basically exploited in case of ground deformations, whereas this amplitude is exploited in case of digital elevation models. This we will see further. Now, we take some examples of different sensors on board of different satellites. Some are still functional, some have completed their lifetime. So, if I take the example of say ALOS pulsar, which is a Japanese sensor, it works in the L band and the wavelength is 23 meter. And whereas the most common band in for SAR interferometry which is used is started with ERS, then ERS of European Space Agency, then radar set of Canada, then NV set of again European Space Agency. SAR is the name of the sensor. Then RISE set does not have the capabilities of acquiring interferometry data. However, the Sentinel is having capability of acquiring data. One more advantage with Sentinel-01 is that the data is also available free of cost for any part of the globe, wherever the the pairs or interferometry pairs are available. Those will be available once data has been acquired, and through internet anyone can download. And another thing, if one would like to do further in this one, then the processing softwares is also available through this European Space Agency. So, you get the data free of cost, you get a processing software, and you too can generate your own interferograms, maybe developing a digital elevation model at high spatial resolution, or you may study ground deformation induced by many factors. There might be X band, which is quite close to the C band, which is 3 centimeter, and Terra SRX is there, and other are there. Some satellites are in the military domain, for which we do not have generally a lot of details available, neither the data. Now, which image, how image should be selected, or the data set, the pair should be selected for SAR processing. While doing this selection, what are the things we should look in that? So, the first step basically the selection of SAR images, which should be suitable for interferometry, and we take them, this pair, for processing. So, the key steps in this criteria which is adopted for the selection of a pair have a strong impact on the quality of our final results. And these criteria, which we are just going to discuss, will depend upon the specific application for which SAR interferometry images are required. That means, if I am going for digital elevation model generation, then I will look these criteria a little differently. When I am going for ground deformation studies, then I will look these criteria a little differently. So, two most important SAR applications, as I have already mentioned, one is the digital elevation model and another one is the differential interferometry, or detecting the ground deformations. So, in order to have the best results from our analysis of SAR interferometry data, the following parameters are important. The first one is the view angle, and this we will discuss further on this aspect, that ascending and descending passes, because half of the globe is covered through the ascending pass, and half of the globe, the other side of the globe, will be covered by descending pass. So, are these passes making any difference in our results? That is the through different view angles we will be seeing in, or we will be discussing about this part. Then geometrical baseline, as just I have discussed, the perpendicular baseline is important, that part we will be also taking further. Then temporal baseline, the time difference between two scenes. If time difference is too big, there might be some changes on the ground, and whether those changes were expected or they are the changes which make create problem for our analysis, that one has to see. Like for example, if I am using this SAR interferometry technique to detect the ground deformation induced by an earthquake, then I want the closest scenes, two scenes in between the earthquake might have occurred. So, in that way, generally these overpasses time or repeat cycle or temporal resolution of the satellite is 35 days. This is how these orbits have been designed. So, in between, if two scenes I am having, one is pre-earthquake, another one is post-earthquake, then I will have a lot of control or confidence in my analysis. So, temporal baseline should not be too big, otherwise the level of confidence in my results will be very less. Time of the acquisition of data, and generally the time here means not the time of the satellite overpass, because we are not operator of the satellite. For us the data is being acquired and the overpass time over area is fixed. Time of the acquisition means that basically here the season, that when suppose pre-monsoon and post-monsoon. Now, vegetation condition is going to be completely different in case of Indian terrain. So, that thing should also be kept in mind while selecting the data pairs. So, timing should be seen in that perspective. Then the coherence, of course, the coherence information will only come once you have started analyzing the data. So, in very first few steps you can have assessment of coherence. We will also discuss this part in little detail, maybe in this discussion or maybe in the next. Then meteorological conditions. Meteorological conditions sometimes can bring the changes because what through SAR interferometry, especially ground deformation studies, we are looking the changes of millimeter or centimeter scale, and therefore any big differences between meteorological conditions of two scenes or a pair may give little different results, and therefore essay basically how to attribute that those changes are purely because of ground deformation rather than changes in the meteorological conditions between those two data acquisition dates. So, that also if that information is also available, that should be utilized while selecting the imaging. Now, first about the ascending and descending passes. So, as I was telling that ascending passes when from south to north the satellite is going, and as soon as it passes over the poles then or near poles, it will go on the other side, that is going to be the descending. So, half of the globe will always be covered in ascending mode, other half will be covered in descending passes. So, however, these things can bring little changes in our analysis. So, this is what we will look through this figure. Then when we are having the ascending overpasses, then what we are seeing here, this LOS stands for line of sight, in which direction the satellite is looking towards the earth. So, the changes from far from the satellite, that means say the changes, if no changes in the color, that means there is in this I am talking about the fringe map or interferogram map, which will be generating after the processing. So, if there is no change in color, means I am not observing any fringe which is showing different colors, that conclusion is that in between those two dates and no change has really occurred. If I am seeing some changes in the colors, a single fringe I am seeing here observing, then there is a change in the line of sight. So, line of sight means if the ground either has gone down or up. For example, here the subsidence will bring this kind of change in the ascending overpasses, whereas in case of descending, this same subsidence may bring changes something like this. So, there is hardly any difference. However, when we see that the change far from the satellite, this LOS change, then the multiple, if there are multiple fringes, then the fringes will have different colors, which you can see here the pattern. If I go from left to right, then I am having different colors, cyan, magenta, yellow. Here I am having yellow, magenta and cyan. So, that way I can see the changes due to the ascending and descending passes. So, no deformation, no fringe, no changes in color. Some subsidence, some deformation, I will see a big fringe, and then I in the both the cases, and it is very difficult to see any changes due to ascending or descending mode. However, when changes are like this, like a thrust or something which is in east-west direction, the deformation has occurred due to some earthquake event, tectonic event, then I will be seeing the changes in the, I will be seeing the colors of fringes like this, that cyan, magenta, yellow, in this case yellow, magenta, cyan. Now, this is the line of sight which you can see, and this is the direction of the satellite which is going like that. In this, whereas in the descending mode, of course, it is opposite direction of sight and line of sight in this direction. So, when a satellite is looking this way or the satellite is looking this way, that may bring, because the same structure of the earth is being looked with two different look angles through these ascending and descending passes, and therefore, they will have different interferograms which you can see here. one important point I would like to also mention, when ground deformations are in a large area but small, like the middle example that is say subsidence, that a large area is getting subsided but the magnitude of subsidence is little, and you would see the fringes very open kind of fringes like you are seeing in this middle case. But when deformations are occurring in a small area but magnitude wise they are very high, like in the bottom example, then these fringes will be very close. And also by counting the fringes and divided by half the wavelength by 2. So, if a wavelength is say 5 centimeter or 5.6 centimeter, then 2.8 the value which is half of the wavelength and number of fringes. So, in this case if I say that this is a C band and data acquisition, I have got 2 clear cut fringes in the bottom example and I multiply by 2.8, that means the deformations have occurred of equivalent to 5.6. So, in that way the magnitude of deformation can be assessed, can be estimated based on the number of fringes which I get, and in how much area, that also can be seen here. There is only one fringe in the middle case, so I say that only deformation and that 2 is subsidence of 2.8 centimeter. Whereas in the bottom example I am seeing deformation in the line of sight. This one has to remember, this is deformation is line of sight because the ground either has gone down or up in the line of sight of the data acquisition. So, in the bottom example the deformations are of magnitude of 5.6 centimeter. So, these plays very important role while assessing the quality. Now, another important aspect is the coherence. Like in this example which we are seeing, that wherever we get these no clear cut fringes, only a speckle kind of characteristics in interferograms. If you see a very larger scale, there is a one fringe which is very clearly visible, but rest of the areas you do not have any fringes except these speckle characteristics. So, these are the incoherent areas which are marked here, and the coherent area is this one which is showing just one single fringe. So, areas basically without clear fringe pattern represents incoherent areas. Now, incoherency can be occurred because of certain reasons. So, basically the same pixel, because we are having now a pair. So, a pixel should reflect radio waves in almost in same condition between 2 observations of two pixels from 2 images. So, that should have the same reflect radio waves in almost the same condition. When the displacement within one pixel is uniform, then good coherence can be obtained. But when this is not there, then you do not get good coherence. Like for example, in case of water surface, interference cannot occur because the water surface varies with the fluctuation of water with the time. So, if there is a 35 days time difference between 2 images, which is very common, then the water condition, the surface conditions of water will be different, and therefore, we may not get coherency in our analysis of these 2 scenes. Even if displacement within a pixel are small for extracting from 2 images, but the ground surface is inclined like in mountain areas, then interference cannot easily occur when the distance between 2 observation positions of the satellite is large. So, these are some of the reasons which may create problem in coherence to get coherent, and once if you do not have the coherency in the scenes, then interferograms cannot be derived. So, if like in this example on the left figure, incoherent areas are there, but they are in one side and they are very clearly coming up, whereas coherency has been observed in a large area, though there is only hardly we can count only one fringe. So, one fringe generally cannot be concluded that ground deformation has taken place. Sometimes the errors which may contribute up to one fringe. So, that can be in that if I start interpreting this result interferogram, then I can ignore if I am getting in a large area one fringe which is spread in a very large area of the scene, then I can say that this might be due to some errors that might be because of meteorological conditions or might be in processing or other things. So, this brings to the end of first part of SAR interferometry. In the second part, we are going to discuss applications and other intricacies in it. So, this brings to end of this discussion. Thank you very much.